You ever feel like you're getting scientific whiplash? One day a study says remote work is amazing for productivity, and the very next day, another one says you have to be in the office. It's confusing, and it makes you wonder, what can I actually trust? Well, the truth is, a single study almost never settles anything. The real answer is always in the bigger picture. Today, we're going to look at a really powerful tool that's designed to find that truth. And we're going to uncover a hidden flaw in how it's being used that could be threatening the very foundation of scientific research. So, here's our game plan. First, we'll talk about why one study just isn't enough. Then, we'll introduce a tool designed to find the real context. We'll see how that tool is often used incorrectly. Then, we'll cover the rules for doing better science. And finally, we'll see why picking the right model literally changes everything. Let's get into it. So let's start with the big question. Why can't we just trust a single study? Well, because the world is messy. It's complicated. Science isn't about finding one clean, simple answer. It's about trying to make sense of all the noise and all the variation out there.
Let's just take this really common question. On the surface, it seems simple enough, right? But the answer you get really depends on who you're asking, what kind of work they do, and where they're doing it.
And this is what you get. Headlines that seem to completely contradict each other. That first study might have looked at a team of software engineers, while the second one focused on a highly collaborative ad agency. See, both findings can be true, but only within their own little world. Neither one is telling you the whole story, and that just leaves the rest of us feeling confused. And look, this isn't some new problem. Researchers were pointing this out decades ago. Science has always been about accumulating knowledge over time, from lots and lots of studies. Think of each study as just one piece of a giant puzzle. The real goal is to see how they all fit together. And to fit those pieces together, scientists look for something called boundary conditions. It's a fancy term for a simple idea: context. It's the when, the where, and the for whom a certain finding actually holds true. Finding these is the secret to solving all those contradictions. Okay, so if finding these boundary conditions is so important, scientists must need a special kind of tool to do it, right? They do. And that tool is a really powerful statistical technique called metaregression. Now, the old way of doing this, subgrouping, was, well, it was kind of clumsy. It forced data into these crude boxes, like high motivation versus low motivation. But metaregression is a huge leap forward. It can look at factors on a whole spectrum, and it can test a bunch of conditions all at once. It's just way, way more precise. Here's basically how it works, in 4 steps. First, it pulls together the results from maybe hundreds of different studies. Then it looks for potential boundary conditions within that data, things like how complex a job is or the size of a team. Third, it runs a sophisticated analysis to see which of those conditions actually makes an effect stronger or weaker. And finally, it pinpoints the exact context where an idea really matters. Think of it like this. If a single study is like trying to explore a huge, rugged landscape on foot, metaregression is like having an all-terrain vehicle with a high-tech GPS. It lets you cover massive amounts of ground with incredible precision to see the entire map. It is a total game changer for science. So we have this incredible, powerful tool that can help us find the real truth. It's fantastic. But what if I told you that this high-performance vehicle is being driven badly? This is where we start to uncover a hidden credibility crisis. So a couple of researchers, Eric Gonzalez-Muley and Herman Aguinis, decided to look under the hood. They took 63 of these metaregression studies, all published in top-tier journals, to see if scientists were actually following the best practices. And what they found was pretty shocking. First off, a staggering 67%. That's 2/3 of all the studies didn't even bother to report which statistical model they used. That is the most basic choice you make. It's like a chef giving you a recipe but leaving out whether you're supposed to bake, fry, or grill the food. It makes the result totally impossible to check or evaluate. And it gets worse. A full 78% didn't report the basic correlations between their variables. Not sharing this is a huge red flag because it can hide all sorts of problems in the data. But this one is the real kicker. The number of studies that actually checked if their data set was big enough to even find an effect in the first place? 0. Not a single one. That means researchers could have concluded that no context matters, simply because their analysis wasn't powerful enough to find it. So what does this all add up to? Well, the authors themselves put it pretty bluntly. They said that because of these failures, many published findings are, and I quote, ambiguous at best and potentially misleading. This isn't just about sloppy paperwork. The actual results of the science could be flat out wrong. Okay, that is a serious problem. But there is a clear solution, and it all starts with one absolutely critical choice that every single researcher has to make. And that choice, the one that 2/3 of studies didn't even mention, is whether to use a fixed effects model or a mixed effects model. This one decision can completely flip a study's conclusion upside down. Okay, let's break this down. The fixed effects model makes this incredibly bold assumption. It basically says, I have found every single factor that could possibly matter. It's really prone to finding false positives. Then you have the mixed effects model, which is just more realistic. It assumes, hey, there might be other factors out there we don't know about. It's more cautious, it's safer, and it's the right choice in almost every case in the social sciences. So does this kind of technical choice really make a difference in the real world? Well, the authors decided to run a little experiment. They took the exact same data set and analyzed it twice, once with the wrong model and once with the right one. They looked at a pretty classic question, the link between being an extrovert and being satisfied with your job. And they tested if that link was stronger in jobs that involved leading others, having a big impact, and having a lot of contact with people. Seems pretty logical, right? Now look at this. The top row shows the results using the wrong model, the fixed effects one. And the results are beautiful. All 3 job characteristics come back as significant. It's a clean, exciting, super publishable finding. The conclusion seems crystal clear. If you want happy, extroverted employees, give them jobs with leadership and lots of social contact. It's simple, actionable advice for any manager. But it's probably wrong, because when they ran the exact same data through the correct model, the mixed effects model, poof, it all disappeared. None of the factors were significant. Not a single one. The exciting finding completely vanished. The conclusion is the exact opposite of what they found before. So this is the crucial point, and it's so important. Wrong method, wrong conclusion, and wrong real-world advice. This isn't just some nerdy academic debate. The choice of model is literally the difference between finding a scientific truth and creating scientific fiction. So let's just quickly recap the big takeaways here. Metaregression is a super important tool, but the way it's being misused is a real threat to the credibility of science. That one choice between a fixed effects and a mixed effects model can completely reverse a study's findings. And finally, being transparent about your methods isn't just a nice to have. It's the absolute bedrock of science we can actually trust. And all of this leaves us with one final, kind of unsettling question to think about. How many of the scientific truths that we just take for granted, the ideas that shape our businesses, our policies, our lives, might just be built on the fragile foundation of the wrong model?